So let me introduce today's speaker. We have a pleasure to host André-Marie Tremblay from Sherbrooke University. So his PhD was from MIT, and then he did postdoc at Cornell and became full professor at University of Sherbrooke, where he rose in the ladders, and he's currently a chair in the department. He has a long list of awards and membership. For example, he's member of the National Academy of Sciences Canada, and he's extremely well known for his work on high temperature superconductivity, in particular on cuprates, and he will talk about his latest work on superconductivity in ultra quantum matter optimizing TC. So please, André-Marie.
Okay, thank you very much, Christian, with this nice introduction. It's a bit embarrassing. I hope I can have the pleasure to reciprocate. Yeah, it's like this this story that says that you have to go to your friend's funeral if you want them to come to yours, right? Yeah, sorry that I would have loved to go to Rutgers. I still have my Rutgers cup, as I was showing earlier, but unfortunately, as you know, the times are not appropriate for this. So welcome to superconductivity.
If I may, André-Marie, please,
yes.
could you switch your to full screen? I think you're showing another type of screen.
Ah, you're right. Sorry, I made this mistake.
Yeah.
Screen number 1, number 2. No?
Oh, it's right.
Is it okay now?
Yes.
Okay. I thought I had done the test, but somehow. Okay. So ultra quantum matter is a bit of marketing, as you will see, but I'll try to explain what I mean by this. So superconductivity is interesting for applications, obviously, and transporting electricity without resistance from region with the sun to do solar power to less fortunate regions as far as sun is concerned, and then making magnets for medical imaging, or this levitating train for high-speed train in Shanghai, or devices for quantum computing. So can we have superconductivity at room temperature? And all these applications would become more standard, and you would have many more that I didn't have time to mention. So here's the state of the art. So this is the critical temperature as a function of the year of discovery for various classes of material that are coded with color-coded. So we have literally almost a room temperature superconductivity, but these pressures are of the order of the pressure at the center of the Earth, so it's not so convenient. So what I'm going to talk about is this class of material here in blue. That was the first class of material whose transition temperature exceeded the liquid nitrogen boiling point. So their atomic structure differs from one compound to the other, but the most important aspect is that they have these copper-oxygen planes. So oxygen is in red and copper in black in this picture. And so the rest of the material here has a lot of things to say, but for now, let's say that the only important thing is that it takes away electrons, so it puts holes in that plane, or it puts electrons. So it's for us now, it's mostly doping. So the phase diagram that you obtained is a function of temperature and hole doping. Looks rather complicated, although it has some aspects of universality in this class of material. So at 0 doping, which means 1 electron per unit cell, so that's half filling, you have an antiferromagnetic insulator, and then you have all sorts of phases that I will not talk about in this talk. But the methods I will describe have something to do about many of these. So I will focus on the superconductivity, or this so-called superconducting dome. So who ordered this? It's rather perhaps this sort of devil. But we can flip the question also, which is who's looking into this? And then there's perhaps this is what the old physicists like me start looking like if you work on this problem for too long. Whoops, sorry. So it's a highly quantum mechanical problem. So if we look at modeling this copper oxygen plane, assuming that all the other electronic states are far from the Fermi level, then a simple model is a model of electrons hopping from one unit cell to the other, and having a large cost in repulsion or screen Coulomb interaction when you're in the same unit cell. So in other words, there are two terms in the Hamiltonian. This one here describes all these hoppings and is diagonal in the band basis. In other words, plane waves basically diagonalize this piece. On the other end, if the interaction is very strong and this dominates, then the ground state is that you have to put electrons alone by themselves in these unit cells. They don't want to step on each other. Now, if you are at half filling, in other words, one electron per unit cell, then if this U is sufficiently large, you can see that you will have an insulator. So you can have a metal insulator transition, and that will be called a MUT insulator. So in the regime, we are interested in these two terms, the repulsion and the band, whose width is about 8 times this hopping here. These two terms are going to be of comparable magnitude, which means there's no good basis. There's no, the localized aspects and the delocalized aspects, the plane waves, are really very far from each other. In some sense, this is the embodiment of a particle wave duality in quantum mechanics. So that's why I say it's ultra quantum mechanical. The electrons cannot escape very much. They're moving in one band and they have very strong repulsion. In addition, it's a spin 1/2. As you know, spin 1/2 objects are very most quantum mechanical spins. Finally, I will tell you right away about something we will need later. So let me explain this very briefly. You need to remember this J is 4T squared over U. So if this U dominates, if it's large, then as we said, the ground state is to have lone electrons in each unit cell. And then if you turn on the hopping, you can lower the energy by allowing some kinetic energy if the spins are anti-parallel. Why? Because if the spins are parallel, then Pauli principle does not allow you to doubly occupy that side. And then in second order degenerate perturbation theory, what you do is you return there. So that's a virtual state if you want. And you have lowered the energy for anti-parallel spins. So the outline of the talk is as follows. I will talk about the method, about the one-band Hubbard model very briefly, about D-wave superconductivity. And the main dish is a 3-band Hubbard model, and in particular, what is the role of oxygen. Now we'll show calculations that explain 3 experiments that show how to optimize D-wave superconductivity. And the take-home messages will be this. A detailed picture of the origin of superconductivity in cuprates follows from a model that takes into account copper, oxygen, kinetic energy, and repulsion. And we need to go beyond traditional tools of solid-state physics to work this out. So I didn't say this at the beginning, but you can interrupt me with questions at any time. Okay, so the first thing is to still start with some basis, and a good basis to start with is the one given by density functional theories. I will come back to this later in the talk. But for now, the method I'll be using is dynamical mean field theory that was developed basically at Rutgers with also Antoine Georges and Gabi Cotillard. And I'll be interested mostly in the cluster version of this, which again came from Rutgers. So we said that in these models, you have you don't know if you're going to use a localized or a delocalized basis. You need to treat both together. So let's start with the localized point of view. So assume that I isolate a cluster of sites of this infinite lattice, and that I represent everything else in the lattice just by the fact that electrons can up in and out of this cluster. So if you think of Feynman path integral, either you go directly from here to here, so it's an instantaneous up, or you go, excuse me, through the lattice, and this is retarded. And this retardation comes in this Green's function, and the effect of retardation is called hybridization function. And the hybridization function just tells you how you can hop from there to there through the lattice, basically. So this is a difficult part of the problem. Suppose you have a way to solve this quantum impurity problem. You find a self-energy. And then the concept is that you want to make the localized and delocalized picture consistent. And the way to do this is to copy this self-energy on the infinite lattice, and then ask that if I project back the Green's function on the infinite lattice on this localized cluster, I get the same Green's function. If I don't, then I need to modify the hybridization function. So the difficult part, as I said, is to solve this quantum impurity problem. So there will be two impurity solvers I will talk about. One is exact diagonalization, where you actually put non-interacting electrons around this cluster. And we've been using the code of David's initial for this. And the other one is continuous time quantum Monte Carlo, where you do hybridization, an expansion to all orders and powers of the hybridization. And Christian here was a pioneer in developing this. And we've contributed some aspects to this algorithm with one of his students and himself. And these features are now available in many codes. And we will be using our code, but they are widely available now. And there are many groups using these methods in Europe, in Paris, in the USA, again at Rutgers, and Japan and China. I won't have time to give credit to everyone, but it's a relatively large community. Now, what are the limitations of these methods? How can we criticize them? An advantage, from my point of view, is that long-range order does not come from a mean field factorization on the cluster. Symmetry breaking is allowed only in the bath of electrons that represents the rest of the system. What's included exactly are short-range dynamical and spatial correlations. And what's missing are long wavelength particle-hole and particle-particle fluctuations. And it's good when all the corresponding correlation lengths are small. So either, let's say, at zero temperature in the ordered state or at very high temperature. In the middle, it sort of interpolates between the two, but it's less controlled when the correlation length is large. Okay, any questions on this? So I'll first show you that, remind you that cuprates are doped Mott insulators. So why is that? Let's look at this cartoon here. I plot here the single particle density of states as a function of energy, and assume that you are in the large interaction limit, or the U large. Then there's one electron per unit cell. If there are n unit cells, then there are n ways of taking an electron out and n ways of adding an electron. And these two processes have to be separated by an energy U. So that's the Mott insulator. So if you take a very high energy photon, like 430 eV here, and you send it, then you see that, let me do this more slowly. Sorry, I went ahead of myself. So now, so here you see that you get a single peak. If you're at zero doping here in the Mott insulator, you get a single peak. Now, if I dope a little bit, in other words, I remove an electron here, what happens is I have n-1 states now for removing electrons, n-1 states for adding electron, and the two missing states correspond to putting up or down electron on that side. Then that's near the Fermi level. So let's go back to the experiment. So if I send again my high energy photon, you see that this peak has decreased in intensity. And now you have another peak that grows here. If I go at 2% whole doping, there's a peak that grows. And yeah, now I have the cartoon. And you can see that this is associated with these states, and this one with these states close to the Fermi level. And this goes down more slowly than the other peak goes up. Now, D-wave superconductivity, that's the main purpose of this talk. So let's talk about the one-band model for a moment, and even more generally now about superconductivity. How do we get an attraction mechanism in the metallic state? Suppose I have an electron that's coming and it scatters off phonon, quantized lattice vibration that goes rather slowly. So it scatters. And then the electron is gone, and this is more or less still there. So another electron of momentum minus p can come and scatter as well in a time reversed fashion. So basically what I have done is I've created correlation between pairs of electrons of opposite momentum. And the electrons did not hit the phonon at the same time, so the interaction is retarded. That's what allows you to avoid Coulomb repulsion. Now for superconductivity, you need one more thing, not just these Cooper pairs, but phase coherence. So let's see how you can get the phase coherence. Let's focus just on the potential energy now. So this is the wave function of the incoming pair. This is the wave function of the outgoing pair. And that's the interaction. Let's do a simple mean field factorization. You see now that you can lower this energy if U here is attractive, and if these wave functions here have a phase that's independent of P or P prime. Because if the phase was random, then you would add the random numbers and that would give you 0. But now if you put a definite phase, you can gain potential energy this way. And this is how you build the BCS wave function. Every time you add a pair, you add it with the same phase. So it's a little bit like a coherent states for lasers, where n is the number of photons, and you add the photons with a given phase. So the superconducting state is a macroscopic quantum state. So in this weak correlation limit, what I described is a phonon exchange like this. But suppose I have a repulsive interaction. So these are very old cartoon pictures that I still find useful. So suppose that U is repulsive, then because of this minus sign, if I simplify the gap here, or the pair wave function, and noting that this is a Fermi function and E are positive excitation energy, so everything is positive on the right hand side, and U has to be negative. If U is repulsive, you can still do something, because if you look at the Cooper pair wave function here, and this is peaked around this green wave vector, then if this changes sign, then if delta is positive here and it's negative there, when U is large for this wave vector, you can cancel the minus sign and still have a pairing. And that's D-wave superconductivity, where the phase of the wave function changes, and it's been proven experimentally. Now we're interested in the strong correlation limit. So I will still show a cartoon for super exchange, and we'll discuss a little bit what's perhaps wrong with this picture. So here you have this JS.S. You can look at all the terms in detail, but here just to simplify, let's look at the SZ part. So you get SZ is N up minus N down on one side, and N up minus N down on the other unit cell. Now, if you put the plus and the minus together, I mean the cross terms together, then you get a minus sign. And this is N down, and this is N up on the next unit cell. And you can rearrange this in such a way that the pair wave function here comes out, and that you have this SZ is attractive in the D wave channel. This is not a retarded interaction, so we'll discuss later whether it's good or not. And there was a more sophisticated slave boson calculation very early on by Gadi on this.
Andre, I think your reference to Anderson is 20 years out of date. It should be 1987, probably. Is that what you mean? Or is this a 2007?
Well, there was a 2007 reference that was in Science that was about the mammoth and the mouse. You remember this cartoon?
Okay, but this was certainly not the first reference by that author.
That's right. I mean, the first reference about this RVB was in 1987.
Okay,
right at the beginning of the superconductivity. Yes.
Right. Okay.
Yes. Yes, but I mean, what Anderson found at the beginning with Bhaskaran was S-wave superconductivity, but yeah.
That's true.
Okay, let me summarize what we learned from one band, the D-wave, without any, I mean, I have the slides if you're interested, I'll show you, but okay, there's lots of singlets near half filling in the normal state. Superconductivity is strongest when kinetic and potential energy are comparable. In other words, neither when you're a very large U limit or very small. And you can show that it scales like J at large U. And condensation energy, when the correlations are strong, come from kinetic energy near half filling and from potential energy at large doping, as confirmed by optical sum rule experiments. And phase fluctuations are important for the shape of the D-wave dome. Okay, let's move now to the main part of the talk, which is this 3-band Hubbard model, or Varma-Schmittrig-Abrams basically came up with this at the same time. So this work was done with David Sénéchal and his student, Siddhartha Dash, and 2 of my students, and Patrick was in Rutgers for a while as well, so some of you may have met him. So we go back to the copper oxygen plane, and now we take into account that there are 3 important orbitals per unit cell. So D orbital on the copper, and P orbitals on the atom. And as before, there are upping terms between all these orbitals. And now there are new parameters here that I will play an important role. Is this epsilon P and epsilon D that are basically the site or the energy that it costs to put an electron on that orbital when it's not tied to everyone else. And the interaction will be only on copper. So certainly there is interaction on oxygen, but the p orbitals are much larger, further away from the nucleus, and the estimates are smaller for this. So I think that putting the interaction only on the copper as the first model is a good approximation. So forget about interactions now and just look at the bands. So on the left is the Brillouin zone, and the Fermi surface is these solid lines. And let's move along a path here from gamma, Km, gamma. There are 3 orbitals per unit cell now, so there are 3 bands, right? You need to diagonalize these 3 by 3 matrices. The lowest band is mostly copper. It's in red. And if you look at the bands near the other bands, they are mostly oxygen. And if you focus on the band near the Fermi energy, which is this dashed line, then you see regions that are neither blue nor red. So it means that copper and oxygen are strongly hybridized. And that's why Anderson proposed the one-band Hubbard model. Now, this was the cartoon for the Mott-Hubbard insulator, but what we really have is a charge transfer insulator. In other words, this so-called lower Hubbard band and upper Hubbard band have mostly copper character, but in between there is oxygen. And you can see what epsilon P minus epsilon D means here also, as far as again in this cartoon. And this is what the cartoon to the right, and to the left is a real calculation with at the zero temperature using exact ionization. And this model I will call the Ionic Model, and I will explain a little bit later what this Ionic Model is. What you can see here in blue is the copper partial density of states. And you see that copper is mostly in the lower Hubbard band and the upper Hubbard band. Oxygen in green is somewhere in between. And at the Fermi level, that is this zero here, we have states that are a mixture of copper and oxygen. They are so-called Zhang-Rice singlet band. And red is the total density of states. So I will come back later a lot on this charge transfer gap. So this is what I mean here by this charge transfer gap. Here in this cartoon, it's just like this. Here I really mean the difference between these two bands. Okay, any question?
Yeah, let me ask one just to get discussion going. Of course, historically, there were huge arguments between these two groups, the three-band model groups and the one-band model group. We saw them here in New Jersey at the time. So obviously a three-band model has much more Hilbert space. It has, after all, a Hilbert space that is 4 cubed. And so it has immense richness to it. And you can add lots of bells and whistles. But what would, if you had to give a Wilsonian RG type argument for why it's important to keep the three-band character, what would you say is different about it?
Okay, you will see that at the end, the results of the three-band model are pretty close to the one of the one-band model. So indeed, this scales to the one-band model. But I will try to show you that looking at the oxygen, which is sort of getting a lot of details inside the unit cell that you may think are irrelevant, in fact tells us, you can see it as a witness of what's happening. And that's basically you're really hitting the crux of the matter. Actually, this is the important question.
Is it that there may be certain interactions that aren't naturally? Is it a more natural way to describe the problem, or does it actually feature new interactions or new qualitative physics that isn't compared in the simple one-band reduction?
I would say that qualitatively, the results is very similar, except that what I'm going to tell you about oxygen cannot be guessed from the one-band Hubbard model.
Okay.
I mean, here, what has been recently proven is that the asymmetry between electron and hole dot cuprates doesn't come out right in Hubbard model. Mm-hmm. And the latest DMRG results show that actually the ground state in most of the Hubbard model, especially on the hole dot side, it's not superconducting, it's all stripes. So the ground state is actually wrong if you do it with the best quantum mechanics calculations currently. So Hubbard model, it's qualitative seems right, but when you look at details, it's not. It's like have the ground state superconducting.
Yes, that's right. But as you know, these states are very close to each other, right?
Yes, they're extremely close. But
and indeed, that's what you see in the phase diagram. I mean, there's there are charge density waves and all sorts of things. So one may be, coming back to Pierre's question, one may be missing some small interaction that makes a difference and shifts. So D-wave superconductivity. So that's just the D-wave order parameter. So I'm going to tell you about 3 experimental observations on optimizing TC that I will try to explain in a unified way. So this one is with NMR. These ones are with scanning tunneling microscopy, and this is neutron scattering. So first note that there are different kinds of cuprates. All have copper oxygen planes, right? But the rest of the structure around is different. But we would like to model them by looking just at one plane. But we have to take into account also the rest eventually. So these are the results of nuclear magnetic resonance. And here on this plane here is the canonical phase diagram that you see for cuprates. And what is the domes that are here are for different compounds or for different families of compounds. And what this is meant to illustrate is that for one whole doping, you can get many different TCs. But what quantum mechanics tells you is that if I put one hole in the unit cell, it has a probability of being on copper and a probability of being on oxygen. Now you could use either axis here, but there's a clear trend here, which is that if I look at the maximum transition temperature, I forgot to say that this vertical scale here is the transition temperature. It's a busy plot. One needs to go a bit slower perhaps than what I'm doing. You see that there's a clear correlation between the maximum TC that you can reach within one family and the oxygen hole content. The larger the oxygen hole content for the same total hole doping, the larger the TC. So can we reproduce this? So I start with this Ionic model, where this is my unit of energy. And what's important here, that's the reason it's called Ionic. It's at epsilon P minus epsilon D. So the difference between the site occupation energies is large. And the reason we use this model, which turned out to be not that realistic, is because to do continuous time quantum Monte Carlo, basically you have a narrow sort of a sweet spot, and this is the sweet spot. So on the right is the calculation. And if you look at oxygen hole content that is now on this axis here, right, 2NP, the oxygen hole content. And what's plotted here is TC calculated with these continuous time quantum Monte Carlo. You see that there's again a correlation between large oxygen hole content and large optimal TC. Now, it's not, I mean, there are exceptions. For example, here, I don't know what happened with this set of parameters, but it's off. I should say that every one of these curves you have to think of as another material, right? And so in other words, the parameters are different. So we start from this base parameter here, and we change them one at a time. So the different colors represent a different material, and we move the chemical potential, if you want, or we hold dope them, and we compute the TC. So we recover this correlation. Now let's look at the more realistic models, and then I start with, again, this work of Rutgers. And one of the things is that is clear is that these copper oxygen planes here, and these other layers, they can either dope these planes like this layer here, and they can also tune the value of the parameters in the plane. So watch out, the next picture is going to be ugly. So you're not going to look at all the numbers here in this table. Again, it comes from some work at Rutgers. So the point is that electronic structure calculation gives us values for these hopping parameters, TPD, TPP, all of them, and also for this epsilon P minus epsilon D. And if you look at TC, it varies. That's a maximum TC. It varies wildly between all these compounds. So just for reference, we'll take this compound that I will call the covalent model, because epsilon P minus epsilon D now is small. You see it's 1.64 in the electron volts now, compared with the large number we had before. And the large number that we had before was measured in unit of TPP here, which is like of the order of 0.6 electron volt. And what's remarkable about this TPP is that it doesn't change very much from one compound to the other. So we use this as our unit of energy. Okay, TPP is 1, and then everything is measured in units of TPP. If you look at parameters, how they vary, but not that much basically, by a factor of 2 or even less in some cases. If you stare at this, don't look at T prime over T, but this TPP prime and all these parameters, they don't vary that much, but they do vary. Okay, so this is this covalent case that I just talked about. So compared with the Ionic model, what you see is that the lower Hubbard band is sort of merged with this charge transfer band, and the charge transfer gap is still there. And the parameters now are TPP equals 1 and epsilon P minus epsilon D is 2.3. So that's our starting point. Now, as I said earlier, we vary the parameters one after the other. And every time we have a new set of parameters, we have a new material, we change the chemical potential, we get a superconducting dome. This is the D-wave superconducting order parameter in the ground state. Excuse me. And that's oxygen hole content. Excuse me. Clearly, you see that the domes here have a larger D-wave order parameter if they have larger oxygen hole content. So the optimal D-wave order parameter comes with a large oxygen hole content. Okay, now you see what's happening here. I mean, you're lying, this is going down. Yeah, what happens here is that this charge transfer gap is closing. So when the charge transfer gap is closing, we have to go to this weak correlation picture. And indeed, the TC goes down. So now another way to optimize TC is that with the charge transfer gap. So if you look at these experiments to measure the charge transfer gap as a function of TC max, you see that the larger TC corresponds to this, whoops, sorry, I'm stealing punches here, correspond to smaller charge transfer gap. And here is an experiment from the Seamus-Davis group that measured directly the superconducting order parameter as a function of charge transfer gap, and we get the same correlation. So this experiment is closer to what we do. So let me plot now again the maximum superconducting order parameter. Okay, this is the covalent set of parameters. So I started from the covalent model and I changed one parameter at a time. And this point here corresponds to the maximum superconducting order parameter for the superconducting dome, and this one also, etc., etc. And here is done for the Ionic model. And what's plotted on the horizontal axis is the charge transfer gap normalized by the bandwidth. So what you see is that indeed there's this inverse correlation between the maximum superconducting order parameter and the charge transfer gap. And this is the charge transfer gap closing there. Another thing that you notice is that the covalent model has a larger superconducting order parameter than the Ionic model set. So I will come back to that in a moment. So this correlation was noted before in this paper, except that what was used were the bare parameters, epsilon P minus epsilon D. What I'm plotting is as a function of the observable charge transfer gap instead of the bare parameters. Okay, now are these two different ways of optimizing TC? And now I'm answering partly the question of Piers, which is that in fact, this optimal hole content on the oxygen is correlated. I mean, the value of 2NP, where the superconducting order parameter is largest, is correlated with the charge transfer, inversely correlated with the charge transfer gap normalized by the interaction. And you see that both models now fall on top of each other. Why is it that the oxygen hole content has anything to do with the charge transfer gap? Well, it's relatively easy to understand, it turns out. So what is plotted here is the oxygen density of states, or the partial density of states, if you want. It's the density of state projected on oxygen as a function of energy. So the Fermi energy here is at 0. Now, every color here corresponds to different values of U. And the largest value of U here is, for example, this value. So you see that the largest value of U has the smallest oxygen hole content. Why is that? Because everything that's above 0 here, if you want, is are holes, right? Because it's the states below 0 that are occupied. So large charge transfer gap corresponds to small oxygen hole content. And what I said is that to optimize TC, you need a small charge transfer gap. So you need a large oxygen hole content. So you see oxygen here is sort of a witness of the charge transfer gap. Now let's go to the pairing mechanism. That takes us to the third example, but perhaps there are questions here. Okay, so go on the right-hand side. You see super exchange J now, as we measure in this calculation, as a function of the charge transfer gap. And you see that the J here is inversely proportional to this charge transfer gap for both models, for both the covalent and the ionic model. Now, this is not surprising, because if we go back to this J equals 4T squared over U, we see that we just replace U in the one-band Hubbard model by the charge transfer gap, and then we get basically this inverse correlation. Qualitatively, obviously, I'm not claiming that it's exact. And now you can also explain the difference between the covalent and the ionic model, because clearly for the ionic model, the effective hopping between copper is going to be smaller, right? So it's better to be covalent. Finally, let me plot the maximum superconducting order parameter as a function of super exchange. Now you see that both models fall basically along the same line. And that's what these experiments give for TC as a function of J. And there are exceptions that we can discuss. But there's a trend here clearly of relating the maximum TC with J. So we explained that third experiment. So
can
yes.
you explain the factor of 10 between TC and J, roughly speaking? When J is about 180 millivolts, that's about 1800.
I don't know how to do that. Well,
pardon me?
Gabby, my question was, do you have an understanding of the factor of 10 between J and TC?
No, except to say that clearly you have the superconductivity comes from, it's a highly fluctuating state. So before you can build it, you have to go down in temperature. I mean, that's the only thing I can say.
But, I mean, if you were to think of this in terms of a weak coupling picture, you clearly wouldn't get a linear relationship between J and TC, right?
Well, J is not defined for the weak coupling.
Well, okay, but if I was stupid and did as Schmidt-Rink and Varma et al. Did, or others, I would have used it as a pairing parameter, and I would have, you know, this is not just a linear plot, it's a linear plot that goes through 0, right?
Yes, yes.
So I was wondering whether you could give us any further insight into it beyond the trend.
Yes, okay. Yeah, that's a good point, and I'm coming to this in the next slide, because indeed the mean field arguments that I showed suggest, like you just said, that TC and J should basically be the same, right? In some ways. But let's look at the glue in the weak coupling in the one band model. But before I do one band model, let me go back even to BCS superconductivity. So electron phonon superconductivity in lead. Okay. So here what is plotted is the imaginary part of the anomalous self-energy. So the imaginary part, if you want, of the Cooper pair, or the self-energy for Cooper pair, as a function of frequency. And this is measured by tunneling experiment, and you see that there are two peaks. Now, if you take the phonon density of states and you shift it by the gap, you see that again you have two peaks. And if you look closely, you can see harmonics of the peaks here, which correspond to the fact that the BCS equation is nonlinear. So, I mean, this was sort of the smoking gun experiment for phonon-mediated superconductivity in electron phonon systems. So back to our problem in the one-band model. So again, I plot the imaginary part of the Cooper pair self-energy as a function of frequency. And again, there are two peaks. So, and then if I plot, now this time not the phonon density of states, but I plot the local spin, the imaginary part of the local spin fluctuations. In other words, the spectral weight for spin fluctuation, double prime. You see that there are two peaks there. Actually, I think Christian was the first to see these two peaks. And you see that if I sort of shift by the gap here, I get that these peaks follow each other. So you can conclude from this that what's imprinted in the pair wave function is this are these spin fluctuations. And if now you look here in the overdope region, you see that this low frequency peak in the end disappears. The red is in the normal state. And that's what's observed experimentally. The maximum of double prime at the lowest frequency, which is here a few millivolts as a function of TC, then it goes down. And I will tell you, I can tell you more about retardation a little bit later, but the message I want to give here is that the simple mean field picture we had at the beginning with J is not quite correct. I mean, there is retardation. We get two bonus results. I mean, one of them is that in the experiment, TC and the total hole concentration are not well correlated. I mean, you see the optimal TC here is for 0.3 doping, and here the optimal doping is around 0.15 doping. And indeed, if we calculate the value of the maximum superconducting order parameter for all these different models, as a function of total hole doping, you see there's no correlation. Another bonus result that was in fact suggested a long time ago in '95 is about the importance of covalency that I tried to demonstrate as well. So if you plot the affinity energy of first row transition metals, and you plot the ionization of energy of oxygen, that's this black line here, you see that copper and oxygen are what forms the strongest covalent bond. So to summarize and conclude, so optimizing TC means, in this case, spin 1/2, one band, two dimensions. Two dimensions favor strong covalency. And I suppose one should look at other chalcogen and transition metals that could have a strong covalent bond. You have to be where the charge transfer gap is just opening, there was an intermediate interaction, and a large value of J at half filling, and more. So for example, these two papers here use data mining and artificial intelligence to go through various compounds and find ways to find compounds that could be a high temperature superconductor. And this work as well. And they even propose a specific compound that could be optimizing TC. So I think that there's the message is that there's hope to be able, I mean, with lots of people and a big effort, it's not trivial. There's hope of designing a high temperature superconductor in the sense that we understand more and more what's going on. So thank you.
Thank you very much, André-Marie, for this great talk. So now we are open for questions. Yeah, first, yeah, open for questions. Pierce already asked few. Any other question?
Maybe I can just get everything going. Just to step back, so you've highlighted the fact that the three-band model can delineate between D doping and P doping, which I think is very, very interesting. So,
but the one-band model does also, I mean, because the band structure is not particle also.
Yeah, there's different T prime, yeah. But superconductivity is wrong. I mean, in the sense that it's small on the hole doping and large, well, somewhat larger in the electron doping.
That's right. But if you look at the electron dope side, the antiferromagnetism is really in the way. If you include antiferromagnetism, that's what seems to be killing superconductivity on the electron dope side.
Do you have any insight into how much you can actually reduce the model's Hilbert space and still keep this essential physics? I mean, obviously, a full-blown three-band model has 4 by 4 by 4 has an immense number of 4 to the cubed number of Hilbert states per unit cell. We'd love to reduce it down below that. Obviously, we don't want to go the full hog of going to a Hubbard model. So where should we stop in between? For example, is it just the Zhang-Rice singlet that's really important here? And can I throw away other symmetries of combinations of P's and D's? Can I make a Wannier state reduction of this problem? Can I write down a strong coupling Kondo model? What kinds of suggestions do you have for reducing the model downwards?
One way that the model was reduced here, even in this three-band calculation, is that the oxygen comes in through a hybridization function, because it's sort of non-interacting, so it can be integrated out in some ways. It's still there, you can measure on it, but as far as the many-body problem is concerned, it's hidden in a hybridization function. That's a trick. That's a trick that was used by Christian and Gabby. I'm sorry.
So if you're fine with working with Lagrangians, it's actually not so bad. It's just like you have Lagrangian for D only, but it has to be Lagrangian rather than Hamiltonian.
Right. And yeah, after that, as I said, at the end, the model looks similar. And if we look at the let me see if I can show one more slide. I don't want to take too much time on the discussion, but let's put it this way here. So let me share the screen. If I can go find where the Zoom is. So, okay. Here, I mean, okay, this is a blow up of this whole diagram here. So what's the blue curve here is a Cadable prime. So for spin fluctuations at pi pi, and you see that they have some typical energy, and you can show that it scales like J. It's not equal to J, but it scales like J. And in black here is this integral as a function of the cutoff. Okay, what does this mean here? If you go from 0 to infinity, that's the superconducting order parameter, the equal time. So in other words, this black curve here is equal to the order parameter in the ground state. And what you see is that the order parameter builds up, it picks up strength here at the same time as the spin fluctuations. And there's an overshoot, and it eventually comes down. So the message is that there's a lot of retardation in this problem. So, but it's there in the one-band model as well. So the one-band Hubbard model has a lot of the physics. I mean, it has the charge order. It has stripes in certain region. It has the antiferromagnetism. It has the D-wave superconductivity. It has the retardation. So what I would say is that doing this foray into the three-band Hubbard model showed us that we can sort of take advantage of the presence of oxygen to tell us what's going on in the mechanism. But if you tell people that the one-band Hubbard model suffices, and they will find exceptions, and I showed you there are exceptions. It doesn't always scale like J, and so you need to do a little bit more, and that's all that we have done here. Nothing more.
Yeah, if I may ask, the issue with one-band Hubbard model, in some sense, is that it seems that when they do very precise calculations for the ground state, it seems that the ground state is almost always, well, it's mostly wrong compared to cuprates. I mean, it doesn't have really, the cuprates physics is not in the ground state, it's in excited states. And of course, if you don't allow the ground state, which is usually stripy-like, if you don't allow it, then the physics is similar to the three-band model probably. But the issue is that there's still something wrong with this Hubbard model, because you always have a stripy face preferred. So I know that this is hard to answer with the tools that we are using or that you are using, but still, do you have any feeling of whether this issue that we have in the Hubbard model, that the stripes tends to be always preferred to the superconductivity, might be overcome when you have the three-band model? Is there any hope that?
Well, you're suggesting an interesting calculation. We have not done it. In fact, the student of David Sénéchal was supposed to look at this stripe or charge order in the three-band model during his thesis, but then he became persuaded, I don't know, by some reason, to work on this first. And then we can, I mean, he's gone now, but perhaps some other brave person will look at the charge order in the three-band model. That's a nice suggestion.
Yeah.
Can I ask a question? Hi, André-Marie. This is Fermi. I had a question coming from someone who's watching this from the side. Is there a dream experiment that you would love to have done that would clarify some of these issues in the cuprates?
You can ask it. I think these experiments I liked. I mean, because
yes.
And then there is some experiment by Seamus Davis who uses the fact that BISCO has a very long wavelength, or not that long, but a long wavelength modulation of the order parameter because of the large density wave. So, and he has precise measurements on the charge transfer gap, and so that's one thing, one calculation we could do. The experiment has already been done. I prefer to ask the question the other way. Is there any calculation we can do that would convince experimentalists?
Oh, I see. Okay, fair enough. Thank you.
Well, experimentalists are now many times extracting self-energy. Of course, I know this is not a very well-defined defined quantity, but nevertheless, they tend to plot self-energy of a normal state quite confidently. So I wonder whether there is any hope to get anomalous self-energy. from Santa.
Yes. Actually, when we came up with this in 2009, I mean, we started to look at whether there would be experiments. Thank you for reminding me. That helps me answer, Premi. So I think that I've seen in the literature, I have to look at this paper in detail because it looks very intriguing. But I think that with they sort of do RPS, I think with 2 electrons coming out, and they hope to get the pair self-energy.
Oh, I see.
Yeah, I think so. That would be
that has a lot of structure in calculations, and if this was confirmed in experiment,
that would be really great. Yes.
Okay, thank you. I didn't even know that was possible to see experimentally.
Yeah.
Well, as I told you, I just saw one paper that I've not read in detail, but I found the suggestion really, interesting. And I hope it can be done. I think it was a theory paper.
I see. Thank you.
Okay, any further questions?
As perhaps I can, as you know, you can measure the pair susceptibility with Josephson junctions, right? It was proposed by Scalapino a long time ago.
Yes.
So yeah, you need to find something clever to access the Cooper pairs directly.
Absolutely.
Can I ask one more question then? What about the normal state? Can your methods give us any insight into the mysteries of the normal state, the strange metal, the Planckian dissipation, if it exists? Can you turn off the superconductivity and give us insights into that from your real-time DMFT?
Yeah, you have to do, actually, we have a paper on that on the archive. And it's done with the DCA and continuous time quantum Monte Carlo, because you have to go at finite temperature.
Mm-hmm.
And if you look at nodal and antinodal patches, you see that near in the pseudo gap, the antinodal patch goes insulating. And then there's a region where it seems to be we get linear resistivity, and it is larger. Slope is larger than the Planckian slope, and the effect of we've looked at the effect of frustration, and it makes it even larger. Now the insight that I have is that I don't think that there is such a limit as a Planckian dissipation. It can be seen just by basically, well, perhaps it's better if I tell you in private, because it will take a
okay, fair enough.
writing. Yeah.
We'll talk in half an hour, so that's fine. Yeah.
Okay, there are no further questions. Then let's thank the speaker again and see you in private.
Okay, thank you very much for your attention.
Okay, so I'll see you, maybe grab a cup of coffee, and I'll see you at 3 o'clock.
Yes, okay, I'll do the same, yes.
Yes, okay, see you.
I was at 3 o'clock. Okay, okay, we'll figure that out.
Wait, I'm at 3 o'clock.
Okay.